Okay, I think the next year, I'm not going to do the same mistake again. I don't tell the students that I don't use that in this record. Okay, I got to be smarter. Okay, so we are discussing how a particular IIT of our country is connected to the upper level layer ISPs. And you say that, up to certain distance of the submarine cables is the ownership of the BSCCL, the local submarine cable company. And then one of the companies own. But it's for routing the data, just for the link to enable the data flow. So that's called IPT, IP transit. So they are providing IP transit, IPT. Similarly, you have here IPT, but then you are definitely getting the actual data from some upper layer ISP. And so these are the ISPs we are connected via ITC. Similarly here, this particular IIG is connected to China Mobile. That's an ISP, upper layer ISP. Whenever you get data services this way, I'm talking about data providers in large scale, then the upper layer service providers are called upstream. I mean the links to the upper layers from where you take data from. And then you deliver service to some lower layer ISPs or some other entities, and that's called downstream. So for this guy, they look at these data links and they call them upstream. When they look at these data links, they call it downstream. But this guy, for this guy, these links are like upstream, this link is like downstream. Now, this is a display of the software tool used by that IAG to live monitor live the data flow on different links. This is Dhaka. This is the router at Dhaka. Okay. And I think all these routers are located in Dhaka, okay, at different points within Dhaka itself. And see, this is the NTTN cloud. It's connected to NTTN. And this is the router in Singapore. Okay, and this is the router in Kolkata. So although it's connected via ITC or submarine cable, but they are connected, on their live tool, they can see all the, routers connected via different links, and they can also see the current data flow on these links. And you see that this one is Google, this one is FB, Facebook, this is Amazon. So these are cache servers. And currently you had, say, on Google 55 point something Gbps data flow. When this, when it captured this tool display. So you can see, and yeah. Yeah. No. This is all, the data flow at that particular moment. Okay, when I took the pictures, they keep changing. So this is the Kolkata. You see that on Kolkata also, Meta means Facebook, Amazon, you have things on different. This is also a router in Kolkata. So within the tool, you can just move your pointer and see different activities at different. So there are different links, and you can see the current data flow on these links. And I'm sorry, but I could not include these pictures in the lecture note because of some restrictions from the particular IID. Now this one shows on some link to Google server. You see the green one shows the data rate in downlink, and this line, blue line, shows the data rate in uplink. Usually the downlink data rate is higher. And this one is shown over some time period, and this is shown for a longer time period. And it is from the China Mobile ISP, the total data from the particular ISP China Mobile. CMI means China Mobile. And you see that the downlink data rate is a lot higher than the uplink. The blue line represents the uplink. Okay. So just to give you some idea. Now NTTN, say, if you have a overhead water tank, and you are sending water to different taps within the building, you may have some thick pipe coming out from the tank, and then onwards there are other pipe network. However, if there is a very thin pipe on its way to a particular tap, then that thin pipe will dictate the maximum data flow or water flow you can provide to the tap, right? Similarly, for data flow, we can have very high-speed link at our, say, Cox's Bazar or Kuakata links where they are landing. But when you're serving someone in, say, in a village in Rangpur, there has to be some high-speed link all the way up to that point. If you may set up, say, 5G base station, okay, providing very high-speed link to the user. But if this base station is not connected all the way to the origin with enough speed, then the data link will be, can you turn on that AC2? Can you turn on or it doesn't work? So this is why you actually need some high-speed data link capacity, so optical fiber-based network to reach different. If you want good penetration, deeper penetration everywhere within the country, then you need actually high-speed optical fiber-based high-speed nationwide network. And there are different vendors who are implementing this project. They are called NTTNs, Nationwide Telecommunication Centers. There are 6 NTTNs, and these 2 are the leaders. Again, Summit has laid very widespread network already. Fiber at Home also has very good network already in our country. Okay. So that completes this discussion. Now we're going to move to IP. IP and the TCP. Any questions? Okay, yeah. Well, this NTTN is something that can be used for any type of service, whether you use for, say, your wireless service, cellular services, or any other, say, you want to set up Wi-Fi at somewhere, some area. This is like a water flow pipe. Okay, that any type of vendor can use that. Any type of vendor will have access to that. Of course, after paying money. No. They rather get money, because these guys are going to charge whoever will get connection from. Again, they are like IPT. No. You have to pay, say, when you use the network of Summit, you have to pay to Summit. Okay? You set up your base stations and take connection from some ISP, from some IIG. You take. Now you need to pay that IIG for the data. But to get the data, you need some link. When you use the link, say, this network of Fiber at Home for NTTN to get the data, you also pay to Fiber at Home. There are multiple vendors that you need to pay to. Okay? They all will make money. Oh, separate. Each vendor, entities have their own separate networks. No, BTRC doesn't have. There are 6. There are 6 entities. I'm not sure, but I'm not sure if when initially there are only 2 entities. Then there was Fiber at Home and Summit, and Fiber at Home laid actually more than Summit. But now there are 6. I'm not sure if BTCL is one of them. It may be. Okay, I had the list actually. Okay, it may be. You can check online. It may be one of the 6. Okay, now, well, he may be correct. BTCL may also be, because when government usually becomes one of the vendors, say from IIG, from IGW, ICX, okay, or say the NTTN. Oh, okay. Okay. Recently started. Okay. So they want to be one of the operators. So one of the 6 entities is then the government itself. Okay. Thank you for this information. Okay. Now the packet routing will be clear once I explain TCP/IP. I mean better clear. When you put many different nodes and form a network for communication among themselves, it's called a network. And different softwares, say software on one device is communicating with software on another device. But there are some processes that have to be done so that these two softwares can talk to each other. They can exchange their information. These processes are layered because some processes need to be done ahead of the rest, or there is some sequence necessary within the processes itself. Some earlier, some later. This is why the processes are layered, indicating which you do earlier, which you do later. On the transmitting side, and the most, the typical, or say the original layering is called for this network is called Open Systems Interconnection, OSI model. But there are many variants of OSI model, and sometimes you split a layer into sub-layers. But the original OSI model looks like this, with 7 layers. On the transmitting side, hey guys, please. On the transmitting side, by application I mean the software. It does the process first, and then forwards its output to the next. Then it does the process. Okay, so every layer does its process and forwards the output to the next layer. So this way, from top to bottom, it flows. And when the physical layer completes its process, it transmits. On the receiving side, the bottom layer receives the information and then does its process and forwards to the upper layer, then upper layer, then up. So this way the software on the receiving side receives. So on the receiving side, it flows from bottom to top. Okay? So just say, for example, you're talking to someone, you just click Mozilla, using Mozilla, you click somewhere on your phone now. It follows this way. Your Mozilla sits on here, the application. Okay? So, now we are going to discuss layer 3 and layer 4. For layer 3, the only solution for internet is IP. Okay. For layer 3, initially there was another solution, X.25, which got obsolete. So, it's IP. That's the solution we're going to discuss today. And for transport layer, there are two solutions, two popular solutions, UDP and TCP. We'll discuss TCP next. Now, how you implement whatever we're going to discuss today. So, IP or the network layer does different things. We'll say TCP does different things. But which part of the system are actually implementing them is the operating system. So if you're running Windows, then Windows implements the TCP/IP. Whatever procedures we're going to discuss this week are actually implemented, are coded in the operating system. It may be Windows, it may be Android, or say Linux. They implement. So, you're connected to different devices connected, then, different applications. No, I'm sorry, I don't mean different device. Different device. And different applications, say, for web browsing, some HTTP protocols that use. Now, the major purposes. Well, IP has basically these two purposes. It takes the packet to the right location, and it uses a postal system approach. Like, you can send letter to any house in the world, because every house is identified with a globally unique address. Like your friend may be in USA, but he has a house number, then a road number, then a city name, then say state, and then the country. So first, some address is given to any user that connects to the network, and that's called IP address. So everything connected gets a globally unique address, and this IP address has a hierarchy. So different, as you route, first maybe like postal system, you look at the country, you send it to particular country, the top level within your address. Then once it gets to the country, it looks at the say state, sends to the state, then it looks at the city. Okay, say from the top level information to the actually lowest level information is used in the address to route. Similarly, here packets are routed, and this routing is done by routers, which can also be called layer 3 switch, because the routers look at the IP address, which is the IP is a layer 3 activity. So since they work on IP layer, it's called layer 3 switch. Router may have let's assume that it has 4 input ports and it has 4 output ports. Each input port has a link to some other router. So from 4 different directions, data is coming to the router. Okay? From different routers, data are coming. Then they are routed towards different directions. You have linked to different routers in different directions. The router maintains a forwarding table which uses a range of IP address. Say, for this range of IP address, it will put the packet to certain port, one of the output ports. And of course, it looks at only the destination address. So you're sending a letter to your friend, the postal system will first look at whatever you address in the address under 2. You also include your own address under from, but that is not used for routing. So similarly, on the IP packet, you include both your destination address and your own address, source address. But routers look at the IP address for a particular range of IP addresses. Okay, it falls within this range, put it on that link, and then it is forwarded to certain other router. So that's how every router reads and forwards, ultimately it gets to the destination. The link between 2 routers is called hop. One hop, then another hop, this way. Completing a number of hops to get to the distance. But the routers can communicate among themselves. They can talk to each other. And based on their own indications, they update the forwarding table. So it can happen that you get some part this way, get crowded now, and based on the suggestions, okay, for the same IP address, you send the packet via this link and get the packet somehow to the same location using some other route. So it can happen because the forwarding tables are updated frequently. Now, you may be sending, you may be talking to your friend on video call and packets are sent. But some packets may go this way and say cross some number of hops, but some other packets go this way and actually encounter different number of hops. It may be a longer path. So the routes for the same communication session, different packets may take different lengths in the route and also different number of hops. So their latency can differ, meaning that you have, when you're sending, an earlier packet may get a longer path and can reach later. A later packet can reach earlier. So the packets can go out of order as they arrive at the base station. So this is very likely. So different packets can take different paths. So this is the feature of packet switching. So when you discuss TCP, we'll see how this, it works on the order correction. But for IP, you just send it to the right location. That's its purpose. It doesn't care whether the packet goes out of order or whatever. So use this IP address for this purpose. This is the IP packet structure. Say from the upper layer, say from station layer, some packets are generated and forwarded to transport layer. So the TCP takes that part, that information as its payload, and then it adds its own header. So TCP header. Okay, and then it is forwarded to the lower layer, network layer. For network layer, this whole thing is like a packet, its own payload. It adds its own header, IP header. Every layer works this way. It generates data and then forward it to the next layer. It is forwarded to, and that is treated as its own payload. And this whole thing is forwarded to layer 2, which may be MAC, medium access control layer. To MAC, this whole thing is like its own payload. The MAC can add its MAC header. Okay. Now, this IP header is typically 20 bytes long, and TCP is also 20 bytes long. And sometimes, in the case of TCP IP, sometimes they are treated together, TCP IP header, which is typically 40 bytes. We'll now discuss the IP header, so you can understand how it is contributing. You see the source address and destination address are just added. This part is the header and payload, and there are some optional fields. Usually they are not present. Now these are the bit numbers. Now you see that the source, the IP address is 32 bits long, right? 32 bits long. With this 32 bits long address, you have to globally identify the users. Now, that actually puts a limit on the maximum number of devices you may have connected to internet. With 32, how many a maximum number you can have, it is 2 to the power 32, right? 2 to the 32 so it's something close to 4 billion. Actually, that number cannot be, all these combinations cannot be used because you need to maintain some hierarchy within the address that you allocate to someone. located somewhere in the world. Okay. So that's how you get some limit. I mean, you cannot use all the combinations, but even if you can do that, it will be a number close to 4 billion. But the number of devices, the required number of devices is going to be even higher, especially considering the IoT devices. So this is why a new version of IP has been introduced with a longer IP address support. That's IP version 6. Currently, this was the IP packet for IP version 4. Only these two versions have been used, 4 and 6. This version field tells what version it is, 4 or 6. And I'll talk a little more about version 6 later. Then header length tells you how long this header part is, because I said that there can be some optional fields. So once you complete the header, you start considering the next bit as your own data. So you need to know how long the header part. So this field tells how long it is. Then TOS is like, some packets you can prioritize for special treating at the router using this field. And then this length field is like, it tells you the total packet length, including the header. Well, because you need to know where any packet starts and it completes. Beyond that, if you have some other byte, they belong to another packet. So the length tells you where this packet completes. And this is a 16 bits long field. So with 16 bits, the maximum number you can have is like 65,000 something. So it tells you how long it is in number of bytes. So the maximum size for IP header can be this many bytes. Okay, it tells you how long. Okay, then you need to go somewhere. Yeah, sure. Okay, and most people are not coming in. At least he has spent some time. Okay, and then there is a protocol field which tells that what the upper layer protocol is, TCP or UDP, whatever. Check some, I spoke of it before, that help you detect whether the packet has been correctly received or not, whether there is error or not. Okay. So it calculates, get the checksum value and puts it here. Checksum, okay, it's a calculation method based on the whole content, including the header. Okay? By considering the enter packet, it calculates. And the result is a 16-bit field, 16-bit number, which is included in the header. The receiver does the calculation, and if it matches this result, then it knows that there is no error. But if it does not match, then there is error. Okay, another purpose of TCP is fragmentation. Well, the first link may have you have some IP packet, and then you want to put on some link. This first link may have a maximum packet size limitation. Like if you're connected to Ethernet. For Ethernet, little bit I'll talk about Ethernet, but I'm not including the Ethernet in our syllabus. Different nodes are connected, computers connected, they are connected to the same hub, so it's actually a common link. And the way they do that, they sense first, whether the link is free or not. When it's busy, it doesn't send anything. But when they find that there is no signal, nobody is transmitting, it can send packet. And if somebody else also finds at the same moment the link free and sends a packet, then these two packets will collide or interfere. So they will be destroyed. So then the nodes actually wait for a random time, back off, wait for random time, and retransmit the packet. But the system tries to minimize this kind of collisions. So this is why the maximum length in Ethernet has some limitation, around 100 meters or something, because you have a propagation delay. If the propagation delay is longer, then you have started transmitting, the other side is still finding the link free, but you actually started transmitting because of long propagation delay. So the length cannot be too much. It's not only the length, but also the maximum packet size. When you transmit, if the packet is very small, then you quickly finish transmitting it. The other side, will not probably collide. But if you have also long transmission, then there are more chances of collision. Okay. So the maximum size permitted in Ethernet is 1500 bytes. It cannot be longer. This is the maximum. Now, IP has a maximum limit much larger. So maybe 30,000 bytes you have used to create an IP packet. But your next link is Ethernet, you find only 1500 bytes. So then you have to chop your packet into pieces and then transmit. But the other side has to reconstruct. So IP facilitates this segmentation, or called fragmentation. And let me show you how it is done. It uses these fields, ident, flags, and offset. Flags have a few flags for indication. One of the flags is used. Flag is just a bit 1 and 0 to indicate something. Now, using an example, I'll show you how it works. Well, in this case, the original bit, right? Forget about my Ethernet numbers. In this example problem, please follow the problem, because in the exam, hey guys, I'm just discussing a problem, and in the exam I very often give problems. So this may be important part of the class today. Okay, so the original packet has 1400 bytes, but when you understand, the maximum size it allows is 512. It cannot be more than that. This is called MTU, maximum transmission unit. Like for Ethernet, MTU is what? MTU is 1500 bytes. Okay? This is called maximum transmission. For any link, communication link, there is some MTU, depending on the protocol. Now the way it is done, here it is 512. So you need actually 3 packets to fit 1400. 512, 512, then you are left with 376 that you put in the third packet. So this is called segmentation. And when you do that, in the first packet, so that the other side can reconstruct, in the first packet you set offset 0, and that flag you set to 1, indicating that this is not the last packet. Flag 1 means it's not the last packet. Offset 0 means how many bytes have already been sent. Actually not how many 8 bytes have already been sent. Okay, then you put 512 bytes. When you generate the second segment, 512 has been already packetized. So you start after 512. In the offset field you indicate what have been previously packetized. But you indicate using, dividing the number by 8. 512 divided by 8, that is 64. So you put here 64 in the offset field. And in the flag, you still set 1 to to indicate that this is not the last packet. Okay. Then you are done with packetizing 1024. So in the offset field, you put 1024 divided by 8, which is 128. Okay. But this is the last packet. So in the flag, you set 0. 0 indicates the last packet.
Can you explain the process of offset?
Offset, yeah. Offset has actually with 8-byte boundaries. All packets are always segmented with 8-byte boundaries. For IP is the policy that always 8-byte boundary. So in the first, when you use the max MTU limit on every early packets. So 512 you put here. But in the second packet, how much have already been packetized? In the earlier packets, 512. So divide that by 8 and 64. Put here 64. But in the third, how much have already been packetized? 512 plus 512. 1024. Divide that by 8. What do you get? 128, right? So put here now 128. But this is the last, yeah. 8 bytes. For IP, the fragmentation must use 8 bytes. Okay? Some granularity of 8 bytes. Okay? And 0 indicates that it completes all the time. However, for all these segments, you use the same number in the ident field. There are another field here, ident. Use the same number. Okay. So a particular packet came in, you segmented, and they all had the same ident fields. Then another IP packet came in. You again chop it into pieces, but now use a different ident field. So using these ident fields, the receiver can separate or distinguish the different segmentations. Okay, so another segmentation will use different ident field. Got it? Yeah. This is just an example problem. Yeah. So this is just an example problem that I do in the class. In the exam, you may get 500 segments. Got it? In the exam, it's gonna be tougher, right? There you may be getting several hundred segments that you work on, and then you get hot-headed. Got it? So this is just an example problem. And then you start using bad words even in the exam hall about myself. No, X just means a number. I mean that the same number. Identities, all of them are some binary numbers. All of them are some binary numbers. You just use a number. This number can be randomly selected. This number, ident field, can have a randomly selected number. All you need that when you do another fragmentation, okay, subsequently you segment another original packet, use a different number there. It just has to be different, that's it. No other requirement. Now IP version 6. Okay, so as I said that IP version 6, to increase the number of nodes that can be connected, okay, it allows 128-bit long address. And with that, it's never possible that you use all the combinations, because as I said, for the hierarchy in according to the location of the node. But if I assume that you can use all of them, then with 128 bits, there are 3.4 into 10 to the 30. I'm sorry, I'll correct it. It means 10 to the 38. so many combinations are possible. So many nodes you can actually connect. Almost every dust on the world. Okay? So this is the IP packet for IP version 6. You see, source address is always indicated, the receiver, so that the receiver, when you send your packet, your friend, okay, just looking at the envelope, knows who has sent the letter. So similarly, the receiver can identify who has sent it. But when you send a query to a web server to download a web page, the web server will respond with its web page content and put it in an IP packet. When you send it to say Yahoo, so Yahoo, the IP address of Yahoo web server will be included here, and your address here. And Yahoo server response sends you an IP packet where it puts your address in the destination and his address in the source. Okay, so it changes. Very importantly, IP version includes the MAC address. This part we are not discussing in detail, but see, for Ethernet or Wi-Fi, their protocols are explained in layer 2. IEEE does not specify anything above layer 2, even when they established WiMAX. The WiMAX protocols are specified within layer 2. When I say that 3GPP has layer 3 protocols most active. Anyway, so this layer 2 is called MAC. IEEE always calls it MAC. That also uses a particular globally unique address. So every Ethernet adapter, the card that you put on your computer, has an address hard-coded. Every Wi-Fi adapter has an address hard-coded on it. Okay? This adapter will have this address hard-coded. And that's a 48 bits long address. It's again a globally unique address. Okay? So that is used for routing within Ethernet protocol or within Wi-Fi protocol. Now, IP version, when you send a packet, you have some IP address, right? In case of IP version 6, your IP version 6 address includes the MAC address itself. Okay. So MAC address is a part, because it is there, you have enough space. This 48 bit is a part of the 128 bits long address. Well, the routing in the local area can be easier. Just looking at IP address, you know actually when it comes to your premise. Okay, it can be routed even with your IP address. You don't need to check you don't need to get to the MAC field. Okay, because when the packets have IP, when you generate IP packet, you have IP address included. And then that is fitted into the MAC, layer 2. Okay. That may not even add the address, it's possible. Because you have to make your address globally unique, right? Since MAC is also helping you do that, why don't you include it? It will not be the same with another user. Yeah. That part already helps you make it unique. Okay. You add some prefix, and then it will be different. That's called prefix in IP version 6. Well, maybe we don't discuss detail for IP version 6, but you don't need. The point is, for IP version 6, the header is longer because it is 128 bits long. So it's 40 bytes. Only the IP address, IP header is 40 bytes long. Okay. 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 It says that your network may support only IP version 4, but the packet has arrived with version 6. How you can make it backward compatible? Okay. It's like that. Then the initial router generates a new packet with an IP version 4 address, and so that is called, encapsulating, or then this IP version 6 packet will be the header, will be the payload of your IP version 4 packet. Then you send it. So this is treated like tunneling. Okay. So anyway, you can check your IP address this way. Just say go to command prompt. Say on your computer, go to run, then type in CMD. It will open this kind of window, black window, CMD. From run. On Windows, run CMD. Then this command prompt will appear. There, if you type in ipconfig and hit enter, it will show you your IP address. If you are using a DHCP protocol, then your IP address can change. Your IP address can be either static, or if it is DHCP, I think here in our campus it is DHCP, your IP address can change. Okay. So if you want to see your MAC address too, then type in ipconfig all. ipconfig/all. Then it will show your MAC address too. So MAC address is sometimes also called physical address. So this this should be 48 bytes. 1, 2, 3, 4, 5, 6. 6 times. Okay. Anyway, it's in hexadecimal. It should be 48 bytes long. And this is the IP version 4 address. Okay. And IP version 6 address you are also getting. I'm not sure how. Okay, now for either IP or TCP, when there is a wireless connection, there is something to do special. So that part I'll discuss inshallah the next day. We may have to take another extra class. Very difficult for me to finish all this stuff. Sorry. I'm Divo.